where were we yesterday? And don't get literal and say right here. Formula on the board, right? What did we close yesterday with? What did we state about this equation as it exists on the board? It's balanced. It's a balanced equation. Okay, pivot point in the middle here. We're looking for balance. This doesn't really exist. It's just my way of showing you this is the pivot point. We're looking for balance. Whereas this side has to balance this side. And when they perfectly balance, it's like getting that other person on the teeter-totter with you, which, based upon the moment arm, which either they weigh exactly the same as you do and they're exactly the same distance from the center, or they don't weigh the same as you and you adjust by sitting closer or farther from the pivot point, right? You get a balance, both sides balance. What we're looking for in chemical equations is a balance between this side of the equation and this side of the equation. Now, just looking at this equation as it exists on the board, let's ask a few questions. First of all, what are the reactants in this equation? Or at least, where do they exist? Where are the reactants? Okay, on the left-hand side, these are the reactants. The reactants are what you start with. They're going to produce what? Products. So the reactants produce products. All right? So make sure we understand the terminology. So when I say look to the reactants or look to the products, where are you going to be looking? The reactants are what you start with. The products are what you produce. Now later on, we're going to get a little fancier and realize that some reactions are reversible. And so you may get a reaction sign later on that looks something like this, meaning it can go back and forth. The reactants form the products, and the products form the reactants, and they go back and forth. That's a little bit later on, just giving you a preview. For right now, let's consider it just to be a one-way relationship, that we have reactants that produce products. Now, hopefully you agree with me that the reactant side includes atoms, right? It includes atoms. But even more than that, there's a little bit more structure here than just atoms. It also includes molecules, correct? So we have molecules which have been built up from the atoms. And the molecule, one molecule is reacting with another molecule, or one type of molecule is reacting with another type of molecule. And when a molecule reacts with a molecule, what we actually have as well at the same time are the atoms within that molecule reacting with the atoms in the other molecule. So all the pieces are going to be reacting in some way. Some decisions are going to be made, not by you or me, but the way God has organized it, in a starting point and an ending point looking different. And in your mind, taking Legos, having each different element is a different color Lego. Each molecule is a structure of Legos using the different colors. And there's a certain number of Legos on this side, and there's got to be exactly the same number of Legos on that side. As a matter of fact, the same number of each color Lego on this side, just built into different structures. Over here, it might look like triangles. Over here, it looks like a square. And I say that not because it physically looks that way, but because that's the concept. We've got building blocks we start with. You know, ever see little kids when they come into a room and there's already stuff built with blocks? They're already built and they come in and they decide, I don't like that, I'm going to make something else, right? And they take all the blocks in the room, they tear them all down, and they build new things. They haven't made any new blocks. They haven't destroyed any of the old blocks. But if they use exactly what they started with and it looks different, that's kind of what happens in an equation, a chemical equation that is balanced. An unbalanced equation isn't going to be a perfect match. There's going to be other things, let's say. There's going to be leftover something. And we'll get into what it means later on to be an unbalanced equation, but for right now, just understanding the concept of balance. So we've got reactants, we've got products. Talk to me about the phases that you see up here. What are the phases of each of the molecules at each point as either reactant or as product? What is their phase? Okay, remember, what does phase refer to? It's the form. Water as ice is a solid phase. Water as a liquid, obviously, is a liquid phase. Water as water vapor is a gaseous phase. And the fourth one that doesn't apply to water, what is the fourth phase? Solid, liquid, gas, and aqueous, AQ. aqueous, meaning whatever it is, it's in water. So aqueous water is redundant because water in water is water. Okay. But those are different phases. So I can look up here and say, well, this is the name for this molecule here, this tetrahedral, is methane. It's a carbon-based molecule. Now that we've done geometries, you can look at that and hopefully see in your mind that this is a tetrahedral with a carbon in the center and 4 hydrogens around it with bond angles of 109 degrees. So this molecule of methane and 2 molecules of oxygen, not atoms of oxygen, molecules of oxygen, right? These are both in gas form. And they react to produce carbon dioxide in gaseous form and 2 water molecules in gaseous form. Water vapor, the common name. Water vapor. So this right here represents a recipe, and later on you might hear me say frequently, we're trying to create the perfect recipe. The perfect recipe for these products is this combination of those reactants. But I want you to understand by looking at this equation, what we're talking about here is actually ratios, not simply the numbers, but also the ratios of the numbers. It'll make more sense when we start talking about moles and other things like that. So looking up here, let's pretend that all we're talking about is the reaction of individual molecules. What I can see by looking up at the board here is that 1 molecule of methane and 2 molecules of oxygen react to produce 1 molecule of carbon dioxide and 2 molecules of water vapor. Okay? Was that my door? Don't think so. Nope. Okay. Yes, ma'am. Okay. So again, looking at the formula, 1 molecule plus 2 molecules reacts to produce 1 molecule and 2 molecules. Now, why didn't I write a 1 and a 1 before the methane and the carbon dioxide? 1 is always implied. The same reason you don't write a 1 is the reason why you don't write a C1H4. Why isn't there a subscript here? It's implied. It's 1 unless you see something else. If it was a 0, it just would not be there. So in order for it to even appear, it has to be at least a 1. In order for the CH4 molecule to appear, there has to be at least one of them. So the 1 is implied. So if the perfect recipe for 1 atom of carbon dioxide and 2 atoms of water vapor is to combine 1 molecule of methane and 2 molecules of oxygen, if that's the perfect recipe, what would happen if I combined 2 molecules of methane and 4 molecules of oxygen? Any guesses? What I've just done basically is doubled my reactants, right? If I, instead of 1 molecule, have 2 molecules of methane, and I double this, and I end up with 4 molecules of oxygen, it's going to react to produce what? Double the products. If I have exactly double the reactants, I'm going to produce exactly double the products. So whereas 1 became 2 and 2 became 4, on this side also 1 becomes 2 and 2 becomes 4. See? What I've basically done is taking all the coefficients here and multiplied them by 2. That's why I said it's a recipe, but it's also proportions. whatever my atom count, my molecule count, whatever it happens to be, I know that 2 and 4 produce 2 and 4. I know that 1 and 2 produce 1 and 2. What if I had a dozen methane? How many oxygens would I need to still have my perfect recipe? If I had 12 methane, how many oxygens would I need? Right, I would need 24, correct. I would need 24 of them to still have my perfect reactants for my recipe. So I have 12 and 24. Now that I have these in the right proportions, I'm going to produce some product. Without the coefficients, what are my products going to be? What molecules should I see on the right-hand side? Same ones I had before, right? I'm still going to see a certain number of carbon dioxide and a certain number of water vapor. But what are the coefficients going to be? Well, 2 times 6. 2 times 6 is 12. 4 times 6 is 24. What do you suppose the coefficients on that side are going to be? 2 times 6 is 12, and 4 times 6 is 24. So what we're saying is the reaction is always going to occur in the same proportions. Right? If I have 1 and 2, it produces 1 and 2. If I have 2 and 4, it produces 2 and 4. If I have 12 and 24, it produces 12 and 24. And this idea becomes real important because later on we're going to use something called Avogadro's number, which is 6.02 times 10 to the 23rd. 6.02 times 10 to the 23rd of this plus 2 times 6 times 10 to the 23rd of that produces 1 times 6 times 10 to the 23rd of this and 2 times 6.02 times 10 to the 23rd of that. Okay? What's the significance of Avogadro's? For us to sit down and count out one atom or one molecule is too small for us to work with. It's way too small. Avogadro's number is a way of taking proportions and putting them into a volume that we can actually measure. So 6.02 times 10 to the 23rd molecules of methane, we can actually put that on a balance and weigh and measure out the mass. And we get to the right amount of mass, we can look at that sample and say, I now have 6.02 times 10 to the 23rd molecules of methane. It's big enough that we can actually measure it. And exactly, it's a little bit later in the course. But you'll be very familiar with that by the time we finish the course. Okay? Matter of fact, extremely familiar with it. It's very important. But we start with the concept of if I have 1 and 2, I produce 1 and 2. If I had a bazillion here and 2 bazillion here, I'd produce 1 bazillion and 2 bazillion. That's the idea of Avogadro's number. It's so big that it's actually something we can see. All right. Quick reminder too, when we're doing the atom counts, let me get rid of these proportionals. These are all correct. But let me go back to our core equation, our simplest equation here. Remember, when we're doing the atom counts, we're saying how many of each atom do I have on the reactant side and the product side. We're going to be looking at both coefficients and subscripts. Remember that when you're counting out the atoms within a molecule, you've got to take the subscript, in this case O2, tells me that every one of them has 2, but I have 2 of them. So I multiply the coefficient by the subscript to get my actual atom count for that element. We've said already that this one is balanced. Let's go through and talk about determining whether or not an equation actually is balanced or not. We've already said this one is balanced, and we finished the class yesterday with proving it. Let's go ahead and do that now and start where we ended yesterday and keep going forward. Okay? So what I said was I see on the left-hand side, I see carbon, I see hydrogen, and I see oxygen. Is there anything else that you see on the reactant side that I missed? No. Okay. So we're going to do an atom count of every one of those elements on the reactant side. And then we're going to do the count for the same things over here on the product side. I see carbons, I see oxygens, I see hydrogens, and I see more oxygens. Okay, so I have every element in both the reactants and the products on there. Now, what would happen? What would I know immediately if I had something on one side and not on the other? It's not balanced, correct? It's unbalanced. You haven't accounted for something. You have come in and played God, and you've destroyed matter. It's gone. Okay? You've taken that and completely obliterated it, which you don't have the authority to do. Okay? There's certain things as a human, no, as hard as you try, people say you can do whatever you set your mind to. It's really not true. Okay? Be reasonable. What does reasonable look like? I'm not going to say go the whole way to Fierro, which says, life is meaningless and doesn't matter what you do, so don't have expectations and live a happy life. That's not where it's at either. But here, you can't destroy, and I'll sometimes say that, you can't play God. You personally don't have the authority to create or destroy the element. But God does give us the authority to rearrange those Legos into different structures. Okay, so on the left-hand side, let's look at the reactants and the products. As I look at carbon, let's assess the number of carbons on the reactant side of the equation. Okay, counting up the carbons, going from left to right. Carbons, how many do I have in this molecule? I have 1. Do I see any more carbons on the reactant side? No, I'm done. I've counted all the carbons on the reactant side. Let's go to the second element I see, hydrogens. How many atoms of hydrogen do I see on the reactant side? Going from left to right, I see 4, correct? Okay, I see 4. Let me count any more. Nope, got them all. Next, oxygen, left to right. Okay, this is the only occurrence of oxygen. How many atoms of oxygen do I have in 2 molecules of O2? I have 2 per molecule, and I have 2 molecules. See? I have 2 sets of 2. So my oxygen count here is going to be the coefficient 2 times the subscript 2, which equals 4. So on the reactant side, in this equation, I have 4 atoms of oxygen at play. Do you see that? Okay. I have 2 sets of 2. And so consider the coefficients in that way. I'm opening the doors because, yes, it may be warm, but half of you are falling asleep because it's warm. So we're going to set up the air conditioner on this side and the heater on that side, and let one side be wide awake, the other side fall asleep. The next day, we'll switch it and watch the same thing happen in reverse. 1 carbon, 4 hydrogens, and 4 oxygens are over on the reactant side. There's nothing else. Every atom is accounted for. Agree? Let's go to the product side. Let's count up the carbons, going from left to right. Okay, 1 carbon. Any more? No. I'm going to do hydrogens because I want to match them with the other side. Hydrogens. Okay, this is my occurrence of hydrogen. I have 2 hydrogen atoms per molecule, and I have 2 molecules. So I have 2 sets of 2. That's the way I'd like you to do it when you do the proofs. I have 2 sets of, think of the times as sets of, 2 sets of 2. 2 sets of 2. See that? So I have 2 sets of 2, which equals 4, and count up the oxygens. Here's my first occurrence of oxygen. It's 1 set of 2. So 1 times 2, which equals 2, right? I'm just going to get rid of that math and just write the 2. So I have 2 of them. And then I have, oh, here's another one. And this one I have 2 sets of 2 sets of 1. 2 sets of 1. I'm looking at the oxygen. 2 sets of, there's an implied 1 there, right? For the oxygen. So in H2O, I have got 2 sets of 2 hydrogens and 2 sets of 1 oxygen. So 2 times 1. So in the first molecule, it's 1 times 2, 1 set of 2. And in the second molecule set, it's 2 sets of 1. So 1 times 2 is 2, plus 2 times 1 is 2, which equals 4. So on the left-hand side, I start with 1 atom of carbon, 4 atoms of hydrogen, and 4 atoms of oxygen that are combined together to make these structures. And after the reaction, I have 1 atom of carbon, 4 atoms of hydrogen, and 4 atoms of oxygen rearranged to produce different structures. Do they match? Carbon, I have 1 and 1. Carbon checks. Hydrogen, 4 and 4. Hydrogen checks. Oxygen, 4 and 4. Oxygen checks. I have a balanced equation. Why? Because every atom I start with is still there at the end. There's nothing more, there's nothing less. It's just rearranged to form different structures. If we looked at it and said, hey, it's not balanced, the numbers are off somewhere, the next step is to, okay, it's unbalanced, you balance it. That's what we're going to next. Determining if it's balanced, and if it's not balanced, balance it. So we are on, let's see. Let's go and determine whether or not, 3rd edition, page 228, 2nd edition, page 121. We're going to determine whether or not this equation is balanced. Again, I'm teaching from 3rd edition. Let me know if the 2nd edition equation is different than the one I put on the board. But the example problem is right here. We're just going to walk through it just as we did this one. It's 2 HCl aqueous and calcium bromide reacts to produce 2 hydrogen bromide with the calcium bromide solid to aqueous. Okay. And 2 calcium chlorides. And the phase given is solid. Okay. We'd expect that the salt. Okay. So we need to determine whether or not this is true. And what it's suggesting is we find out whether or not 2 HCl aqueous, 2 hydrochloric acid molecules in water. You see that? The HCl, you're going to find out that that's hydrochloric acid. The HCl aqueous means I don't have a pure sample of this acid. What I do is I have this acid in water. So it's dissolved in water. The 2 HCl's plus calcium bromide, the salt, in solid form. So what is the, if this was your experiment and you were doing it in the lab, what would it look like? You start with HCl aqueous. Well, that would mean to start that way, you would likely have a beaker that you're going to be doing the reaction in and would have a certain amount of water in it. And in that water, you would have hydrochloric acid. So you would have a liquid hydrochloric acid water mixture in a beaker. And to that, we're going to add some solid calcium bromide. Now, don't worry about anything other than calcium bromide. I hope you can visualize taking some solid chunks of calcium bromide, solid, and dropping it in the acid. And when you do that, there's going to be a reaction. Something's going to happen. And what it changes into at the end is not what you started with. You're going to end up with something that is a rearrangement of the atoms in the hydrochloric acid and the calcium bromide to form this hydrogen bromide and calcium chloride. Let's go through and see if it's balanced the way it is on the board. Okay. I'm going to take what I did before and no, yes, ma'am. Okay. Yep, thank you very much. Yep, thank you. Which we'd pick up either from looking in the book or also remembering that calcium is a column 2A element, right? Calcium is a column 2 element, meaning it has 2 electrons to give away, and chlorine is a column 7 element, meaning each one of them will take one of those. And so they have to pair it 1 to 2. So good, thank you. go through and do the atom count, and rather than have it stretch across the board, what I like to do is set up a little matrix, and I'm going to go on my reactant side and say, okay, I've got hydrogen, I've got chlorine, I've got calcium, and I've got bromine. Okay? Those are the elements that I see on the reactant side of the equation. Now I'm going to look to the product side. I see hydrogen, got it. I see bromine, got it. I see calcium, got it. I see chlorine, I've got it. I don't see anything else. I've accounted for the 4 different building blocks, the 4 different elements that are part of this reaction. Now I'm going to look to the reactant side and the product side and count them up and see if they match. Okay. On the reactants, products, let's count up the hydrogens. There's one occurrence, that's the only occurrence of hydrogen. You agree? Okay. How many hydrogens do I have? I have 2 sets of, how many? 2 sets of 1, which equals 2. We look for chlorines. Chlorines occur here, and that's it, right there. Chlorine, I have 2 sets of, how many? 2 sets of 1, which equals 2. Calcium, it only occurs here. How many do I have? Right, I have 1 set of 1, which equals 1. 1 set of 1. They're not written, but they're implied, so we can kind of visualize them. 1 set of 1. And then I have bromine. Looking across from left to right, that's the only time it occurs. How many bromine? I have 1 set of, how many? 1 set of 2, which produces 2. Okay? So what I'm saying is on the reactant side, I've got 2 hydrogens, 2 chlorines, 1 calcium, and 2 bromines. Now let's look to the product side. After the reaction, we have some things that are produced. How many of each do we have? Hydrogen. How many hydrogens do we have? Looking across the products, it only occurs here. I have 2 sets of 1 for hydrogen. Chlorine. How many do I have? How many sets of how many? For chlorine. For chlorine. For chlorine, I have 2 sets of 2. 2 sets of 2, which equals 4. Calcium. It occurs only here. How many do I have? How many sets? 2 sets of how many each set? 2 sets of 1, which equals 2. 2 sets of 1 to produce 2. And looking here, bromine. How many sets of how many? Okay, it only gets here, correct. Bromine has 2 sets of 1, which equals 2. Let's check to see if they match. Hydrogen, 2 and 2. It matches. Chlorine, 2 and 4. No. Calcium, 1 and 2. No. Bromine, 2 and 2. Is it balanced? It's not balanced because they don't all match. What this is showing me is this reaction is wrong because what I'm doing is out of thin air, out of nothing, I'm creating 2 chlorines and 1 calcium. See, I started with 2 and I ended with 4. Where did they come from? I started with 1, I finished with 2. Where did they come from? They came out of the nothing. Who can make something out of nothing? Only God, not you. You don't have that authority to make something out of nothing. We are artists that rearrange. He's a creator who makes ex nihilo. He makes out of nothing. Okay? So, is that balanced? No, it is not balanced. Yes? If you're asked, is it balanced or not, the answer is yes or no, you do this. More likely you're going to say, is it balanced, and if not, balance it.
So can we balance that, or do you mean just take away?
Can we balance that? That's our next challenge is balancing equations. Page 229 on 3rd edition. And it probably continues on about, 122 on 2nd edition. When we go to balance equations, what I want you to remember is we have the authority, yes, please. We have the authority given to us to change coefficients. We can change coefficients. We can change, in this equation here, we can tinker with the 2, we can tinker with the implied 1, we can tinker with the 2, and we can tinker with the 2. We as human beings, we can mess with the coefficients. What does messing with the coefficients look like? It looks like changing the recipe. Let's say we're baking a cake and 2 of the ingredients are like eggs and flour, okay? We do the recipe and we don't like it, so what do? We add another egg. We decide to try the recipe and we're going to change one of the ingredients a little bit, okay? Now, we can't create something other than an egg from an egg. We can't create a new ingredient out of nothing, but we can change the proportions of the ingredients we've been given. Same kind of a thing. We can't make eggs. We don't come up with the idea of an egg and go, poof, I have an egg, and I'll use it in my recipe. What we can say is God has given me eggs to use, and I used one of them before, now I'll try 2 of them. I'll tinker with the recipe by adding more or less of the things that he's given me that I do have control over. So we can change the coefficients. We can try changing this 2 to a 3 or this to a 1. We can change this implied 1 to a 2. We can do all that kind of stuff on the products and the reactants. We can dabble with it and mix it up and see if it works. But what we cannot do is when we're looking at the structure here, we're not going to have the authority to go in and change a subscript. In other words, I can't come into the calcium chloride, which we spoke about just a moment ago, when Jessa said, you know what, that formula is wrong. That's supposed to be a 2. I can't come in and say, you know what, I need to account for 1 more chlorine, so I'm going to change it from a CaCl2 to a CaCl3. Now, what have you just done if you change a subscript? You've created a new molecule. You've come in and said, hey, calcium, I know you've got 2 extra electrons to give away, but I'm going to pretend that you have 3. Because I need to account for the chlorine taking 3 of those electrons, and you've only got 2. And you're going to force it to break the tech rule. Not going to happen. You don't have that authority. Okay? Or you might come in there and say, I'm going to tell chlorine that it really doesn't need that electron. It should behave as if it does, even though it doesn't have it. It's not going to happen. You don't have that authority. What you do have the authority to do is add 1, 2, 3 more molecules as God has already ordered them to arrange. Okay? So again, if you find yourself balancing an equation and you're messing with the subscripts, you're wrong. Unless, of course, an entire product of the reaction is left off. That's assuming you've got everything, like you've got all the different molecules that do get produced. We'll get a little more nuanced as we go on, but for right now, if you find yourself messing with the subscripts, you're wrong. Have a field day messing with the coefficients. Never touch the subscripts. Right? This is a little bit more difficult than the example that's in the book. I'm kind of hesitant to jump off into this one. But let's go ahead. Just if you don't see this yet, we'll do an easier one next. But since this is already on the board, let's consider, for example, as we look at this here, what do I find that that's not being accounted for correctly? We said the chlorine and the calcium, right? It's not being accounted for correctly. If I look at this and say, okay, chlorine, I have 2 more in the products than I should. To justify 2 here, to justify all 4 here, how many must I have over here? I must have 4, right? To have 4 as the product, I must have 4 as the reactant. How do I get 4 chlorines? Well, chlorines only exist here, right? So if chlorines only exist here, the only way I can get more chlorine here is to get more chlorine here. To get the chlorine here, I can't come in and say, hey, I need 2 more chlorines. Let's make that an HCl3 to give me my 2 more chlorines. Or the coefficient is going to mess that up anyway. I can't do that, right? I can't come in here and say, I have 2, I need 4, so I'm just going to make an HCl2. I can't do that. I don't have the authority to make up a new molecule. But I do have the authority to come in and say, hey, I need 2 more chlorines. How might I get it? Well, let me change this 2 to a 4. Now, how many chlorines do I have? I've got 4 sets of 1, right? And that'll give me 4. 4 and 4 matches, okay? But what else have I messed up with? I've messed up my hydrogen, right? Because I no longer have 2 sets of 1. I now have 4 sets of 1, which is going to give me 4. Which means now hydrogens don't match because I've messed with it. Well, how am I going to get, I've got 4 hydrogens. How do I get 4 hydrogens over here if I've got 4 on the reactant side? How do I use up those? How do I get 4 on this side? Here I've got 2 sets of 1. What might I do? Well, I might consider changing that one too. Rather than 2 sets of 1, let me make that 4 sets of 1. That'll give me 4. So my 2 becomes 4, but I've just messed up my bromine, right? Because now I've got 1 set of 2, and here I've got 4 sets of 1, which gives me 4. And you see, you start to chase the tail. If you say, wait a minute, something's not right. If it's just in terms of balanced or unbalanced, we figured that out long ago. Now we're messing with it, trying to get it to be balanced. 2 calciums, 4 chlorines. The hydrogens are now matched, 4 and 4, but now I've got an issue down here. Calcium. Calcium's here. I have 1, but I finish with 2. What might I do to balance that? Well, I might change the calcium to a 2, but if I change the calcium to a 2 and I balance the calcium, because now I have 2 sets of 1, 2 and 2 match, but I've just messed up the bromine, and the bromine has 2 sets now of 2. 2 sets of 2, guess what? 2 sets of 2 is 4. And 4 times 1 is 4, and now my bromines match 2, and I've just balanced the equation. Well, I encourage you to do it this way first, because now when we look back at it, we can go back and reduce the coefficients, okay? So it's 4, 2, 4, and 2. Common factor of each, all of those is 2. So we could go through and divide all of them in half. This is true. Let me go ahead and erase the work and just write the balanced equation now. We've got the HCl. We had 4 HCl plus 2 calcium bromide produces 4 hydrogen bromide and 2 calcium chloride, okay? That's balanced. We could go back through and say, hey, wait a minute. All these coefficients, that's true. Proportionally, that's correct. Is there a common factor for all of them? Yes, a common factor of 2. I could reduce all of these by dividing them all by 2, and dividing by 2 produces 2, 1, 2, and 1. But you would only be able to do that after you've verified it, and if you do it in this method, you'd build up to that point, and then you could reduce it down. Okay, so it was 4, 2, 4, and 2. Common factor of all those coefficients is 2. Divide them all by 2 and gives me 2, 1, 2, and 1. So if I had, something like 9, 9, 6, 9, 6, I could divide them all by 3, because 3 is a common factor between 9 and 6. And reduce them all down. Right now, if you just came up with 4, 2, 4, 2, I'd be ecstatic. Okay? And then later on, look at it and say, wait a minute, it's also true with 2 bazillion, 1 bazillion, 2 bazillion, 1 bazillion. But So your answer is correct. The most correct would be the simplest, but those others are correct answers too. They're they're true, but they're not necessarily correct or the best. Because we're trying to find the simplest relationship between the molecules on the reactant side and the product side. Okay? So we've actually done a much more difficult one than the first example they give us in the book of balancing this equation. So let's do a simple one. This is kind of a mediocre one or a middle one. Just remember, when you change a coefficient, you've got to go through and change your table for every atom that's in that molecule of which you change the coefficient. You've got to change every atom count.